Everyone, as promised, I'm going to be dropping back-to-back videos. So this is the second one, and it is a bit of a change from the good old code book rules and just explanations. I'm going to shift gears and I'm going to tap into another skill set that, electricians, depending on what you do, right? You got residential guys, you got commercial guys, and you got industrial guys. But either way, a well-rounded electrician should be able to wire anything. It's wiring, right? And know how to apply the codes. But I'm going to shift gears here, and we're going to look at how to create simple control wiring circuits. Now, I mentioned in my last video in the PVC expansions, I am pretty strong in control diagrams, and I do PLC programming and HMI programming, but I do a lot of control circuits. I build a lot of control panels. So I have a good understanding of control wiring. And like I said, as an electrician, this is something that really you should know. It's just wiring, just not in a home or a building. It's still wiring, right? So it's just a different way of coming at it. Okay, so it's just going to be more of a very basic introduction to this. I would like to dig deeper into this, so let me know if this is something you're really wanting to learn more about. I'm thinking about going into how you read relays, like just relays, control relays, how you interpret the symbols on them, how you size them, how you read the ratings, stuff like that. Maybe even a little bit of product review and stuff that I've used, right? But for this one, it's just gonna be very basic, just a basic on how, you take a statement, as you can see on my screen, I got 3 statements, and how to convert that into a wiring diagram. Now, my diagrams are gonna be done in the NEMA standard. There is an IEC standard, which uses slightly different schematic symbols, and their drawings are flipped 90 degrees. If you want to read more about that, you feel free to do that. Just Google search NEMA versus IEC, and lots of stuff will come up. And maybe later in another video I'll touch on IEC, but because I'm in North America, we typically are NEMA based. So that's how I do all my drawings. But back in my maintenance days, I did work as a maintenance electrician in a plant, and 90% of the equipment came from Germany. So I also had to know how to cross-reference and read IEC style diagrams. So they're both out there, even though we're in North America. But predominantly here, everything's done in NEMA. Okay, so very basic. There's lots of stuff that we could touch on. I'm not going to do it here. So if anybody wants to comment and say that's, there's way more to it than that, yes, there is. This is for apprentices, guys that do not do a lot of control wiring because maybe they're just doing residential, but they want to learn how to do this. It's just more of an intro. Okay. All right. So on my screen, I have 3 statements that we're going to do. But before we get into that, let's just kind of go over some symbols. And these that I have actually do kind of give you the different types, NEMA and IEC. And there's a little blurb up here. I'll see if I can somehow post this in the video where you can read it. But again, if you just Google NEMA, N-E-A-M, so NEMA versus IEC, you'll find lots of documentation. All right? NEMA again is US Canadian, and then German definitely IEC. I'm guessing International British would be the same. I'm not 100% sure. Maybe somebody can comment on that. But definitely US, Canada, North America, we are NEMA. In Germany, IEC. Okay, I'm not going to go through every single one, but some that we will be using. So like a coil, right? So everybody knows what a relay is, and if you don't, look it up, Google what is a relay, right? And again, I will do a video later on what a relay is and how they work. Okay, but that would be the schematic symbol for NEMA. And then IEC, it's more of a rectangular look to it. All right, so we get a coil, a relay has a coil in it, we energize it. It basically switches a set of contacts that are internal to it. It's a electrical magnetic switch, we'll call it. Right? We'll talk about that. Fuses, grounding. I'm not going to cover that page. So we will use in our diagram push buttons, right? So this could be a push button that you see on the front of a control panel, right? And these are momentary, meaning you push it, as soon as you let go, it returns to its original state. It doesn't maintain its position that you left it in, right? So it's momentary, okay? So we got normally open. That's what the NO stands for. And if you just imagine on here, you know, current flow, and that is way too big. Let me point that down a bit. Whoops, that did not work out very well either. Get ahead. Let's go back here. Okay, normally open. So what happens when you rest your hand on the pad here? Put this down. Just imagine you had wires connected to this and you got current flow. You got nothing happening here. Just like your toggle switch on a wall in a home or a building, you have no current flow until you close the circuit. So notice that this blade, or this line, does not connect with these two termination points. This switch is normally open, right? When you look at the IEC, very similar, right? If you had current coming down here, well, it cannot continue until this blade made contact with this portion. It's the only way it would continue on, right? Normally open push button. It doesn't show normally closed push button in here. It does for a different style. But let me just show you what a normally closed push button would look like. Okay, so if I had a normally closed push button, you would see the letters NC for normally closed. Right? In this instance, you'd have your two terminals, but your blade would be underneath. Okay? It's normally closed, so as it sits, you got current flowing through it. And this could be going to a relay, it could be going to a PLC input, it could be going to a light in a control circuit. This is normally closed. When an operator pushes this normally closed button, it will open the contacts, interrupting or creating an open circuit. Whereas the normally open, when the operator pushes down on the push button, you close the contacts and now you have current flow. Okay? A lot of times I'll see people draw this symbol wrong, and I'll show you what I mean by that. I'll tell somebody to draw me a normally closed push button, and this is what I'll see. They'll give me the terminals, great, and they'll draw something like this, which is very close. It is close, but there's a gap here. That's sloppy, right? Because there's not only do you have a say normally closed switch, right? This would be normally closed. You also have normally closed held open. Okay? Just like you can also have a normally open switch, right? Normally open. But you can also have a normally closed or normally open held closed. And do you see the difference? The difference is, where is the blade located with respect to the terminals? Is it above it or below it? All right, so that's how you tell a difference if it's normally open, normally closed, and if it's being held open or held closed. Okay, so you really got to watch that. So for example, here's a mushroom head. It's just a fatter head on the button. It's normally closed. The blade is on the bottom side of the terminals. Here's a normally open. It's on the top side. Okay? But you can get them normally open and then held in a certain position, or normally closed and held open. Right? Let's keep going through here. You get two position switches. Right, we're not going to do this in our diagram. So basically, you got two positions on this one. In position 1, A is closed. In position 2, this blade would move down, make contact across the B contacts, and now that's closed. Right, so the X means it's the closed position. You look at the third one here. So in position 1, then you have closed contacts on the B set of contacts here, or yeah, I guess contacts. In position 2, nothing is making contact. So it's like the blade is in between both. And then position 3 where it's at, you can see that A is the closed circuit portion making contact. Right, so that's how you'd read those. Takes a little bit of practice, but that's it in a nutshell. Switches, so you'd find a lot of stuff like this on machines, maybe in wastewater plants or some kind of process control, but you got limit switches. Again, here's a normally open, right? And I like to think of, when you look at these, think of gravity. I know this is normally open, one, because there's a space here, but how do I know this isn't normally closed held open? Because on a push button, the blade is below the terminal. But with these switches, just think of gravity. This gravity's in its resting state. It's just open. It's lowered. Nothing's holding it, right? So that's gone down. So this is normally open. And then here's a normally closed. Again, this is not a normally open held closed. Think of gravity. This is normally closed, and gravity's just kind of letting it push down on its own. Right, so that'd be a pressure switch. You got limit switch. Here's a normally open. All right. Here's a temperature normally closed. So switches are they're opposite than the push buttons with respect to how the blade orientates with the terminals. Okay. Now, I won't get into any current transformers, stuff like that. I just want to cover some basic stuff here. Another page I got over here. Let's see. So just basic contacts. Now NEMA has 2 different standards. I'll tell you, when I'm doing AutoCAD drawings or I'm drawing stuff, I'm using the one on the left. Okay? IEC is just 1. So. But here's a normally closed. So again, it's a switch, just like we had pressure switches and flow switches. When it's a switch, it just orientates differently. I like to use these ones for my contacts. Right? So here's a normally closed contact. And below, we have a normally open. There's an air gap in there, we'll say. Right? Until this switch closes, right? Which usually happens from a coil of a relay energizing, these would close. Then we get into timers. Now here's where I flip on this one. For timers, I prefer to use the ones on the right. Right? And I guess, you could use these here. It says time closed, time open. For these ones, I look at the direction of the arrow. So this is a normally closed. It's still a switch. It's not a push button. And this arrow is telling me that it's timed close. This one is timed open. So this one, whenever the coil is energized for this timer, this will open after a predetermined set of time, whether it's minutes, seconds, milliseconds. So even though the coil energized, there's a delay before this would open. Right? There's a delay before this would close. And same for these ones. Normally open, time closed. Normally open, timed open. Okay? They take a little bit of playing around with to get used to. All right. Indicator lights, they're pretty basic. Almost looks like a coil, but it's got almost like it's a luminescence coming off of it. I kind of like the IEC one better myself, but we'll stick to. You don't want to start mixing IEC and NEMA in the same diagram. You got to stick with one or the other, right? So there's your standard light, right? And pay attention to the note. Usually you'll put the letter of whatever color that light is. So if it was green, if this was a green indicator light, you put the letter G inside of it, or W for white, or yellow. You get Y for yellow or amber, right? Push to test. Basically, I don't know if any of my listeners here do industrial work, and they have the option on a control panel on the front that says push to test, and they push it, and all the lights turn on. That's basically just kind of a PM thing, so you can see which light bulbs need to be changed. Nowadays, everything's LED, but still, same idea. You push it, you're actually turning the light on instead of whatever is ahead of the circuit in its normal state. It could be an output or a contactor turning the light on. You can manually override that and just turn it on yourself. And again, that's a good way back in the day of troubleshooting which light bulbs are burnt out, so that you can do your PM on the panels. Meters, thermal elements, so like in a motor starter, Okay, here's some more push buttons. So you can have push buttons that are illuminated. When you push the button, light turns on. Right. There's a normally closed push button. So notice the blade with respect to the terminals. It's on the bottom side. Okay. Float switches. So again, now we're back to switches. All right. So float switch. Just think of water level here, just like a sump pump. Right. So you got some kind of water level here, and as that water level goes up, this float pushes up and opens up the switch. Same thing works for normally open. Just depends on your application. Right. Same idea though. As water goes up, in this case, we're going to close the switch. Maybe you want a light to turn on, right, when the water level is high, right? Or in this case, maybe you want the light to turn off when the water level is no good, right? It depends what you want to do with it. Flow switches, so maybe you got one of these in an air duct, and it's just measuring to verify that you actually have airflow of some type. Right, so that's normally closed. Here's a normally open. Foot switches. Well, maybe you guys working on a press or machine that you activate a foot switch to initiate the sequence. Right? So then you got limit switches. So here's a normally closed limit switch. It looks just like a switch, right? So if I just had a normal switch, normally closed, the only difference is it's got this little gizmo on the bottom. Okay, limit switch. All right. So just a rundown really quick of some pretty common NEMA schematic symbols. So let's do some of these. Let's see, I'll show you how simple this actually is. Okay, you don't want to overcomplicate it. And again, there's some details I will leave out. For those that know there's more to it, there's just details I will leave out just for simplicity's sake. Okay. So let's look at this one here. So a light will illuminate and stay on if push button 1 is pushed and released. It will remain on until roller limit switch 1 is activated. Right, so what are we looking at here? Okay, so I know I got a light. It doesn't tell me what color, so I can pick a color, honestly. I know it's going to stay on if I push this button. And it will release. So it's a momentary push button. Okay. So light will illuminate and stay on if push button 1 is pushed and released. That light's going to stay on until a limit switch is activated. So most electricians that do control wiring, they should know right away that this is very similar to a low voltage protection circuit. Okay? And for those that program, it's like a latching circuit. So let's draw this out. How do we do this? I'm going to bring this ruler up. I found that I can do this, which is actually really neat. So let's see here. Because one thing that you should always do is make sure your lines are straight. Straight as can be for neatness. So if I go, oh, this is beautiful. Line 1. And I'll put my other one over here. So we call these our power rails. These are our power rails. Right, it's where we get our power from. See if we can get rid of this. And that's basically, you got potential between the two sides. Now in our control circuit, it could be various voltages. Typically, the ones I work on and design, they're 24 volt DC, and that doesn't show up very well. So I'm going to switch colors. Here we go. 24 volt DC. And then this would be my DC COM for common, or you could also call it 0 volts DC, right? Basically, I have 24 volts of potential from this side to this side. You could see control circuits that are also 120 volts AC, right? So when you get working with these controls, pay attention to the voltage. On a good system that's, follows some standards, when you see blue, right, that's typically showing you it's 24 volt system. And when you see red, it's 120 volts. Don't assume it though. Always use your meter. Check the voltage and verify that. Okay? But we always have power rails. Alright, so there's a power rail. And again, for NEMA, they are vertical. Okay? If it was IEC, you just flip this 90 degrees, you'd have your potentials at the top. 24 volts on the top line, and then DC either at the bottom of the page. Yeah, probably at the bottom of the page, because I do believe I've seen 240 volt control as well, so they'd have both lines at the top. Something like that. Again, I'm more of a NEMA guy. But regardless, you'll have power rails of some type. Okay, I'm going to bring this ruler back out. Hopefully I think I can get this to turn. Yes, there we go. Again, straight lines, because you could be drawing this out for somebody and passing it off, right? So you want them to be able to read it. So the first item I see is I got to push button 1, and it tells me that the light comes on when I push it. So if I don't do anything, the light's not coming on, right? So it's got to be a normally open push button, right? So I'm going to bring 24 volts of potential, and I want to go back to my, actually, you know what? I'm going to leave that blue, and I wish I made, I'll keep this one gray. I wish I made everything blue. But I got 24 volts of potential. I'm going to leave a little space because I'm going to put my push button in here. Now, it tells me that when I push this push button, you know what? I will just do it now. I'll put my push button in. All right, I'll try and draw this one somewhat neat. All right, so I'm going to bring 24 volts to my first terminal. And here's my other side. And I told you that it's going to be a normally open push button. Okay, so I'll draw right up here. Normally open push button. And I'm not going to take too much time to keep turning this wheel. All right, so I'll just draw my, I'll just freehand that. And maybe I can cut off some of this because that bugs me. There we go. Okay, normally open push button. There's one thing I should show you. Well, first, you know what, let's finish this diagram. So, normally open push button. And it tells me that a light's going to stay on until a limit switch is activated. So I did allude to that this is going to be similar to a low voltage protection. So this tells me I'm going to be energizing some type of coil, and then it's going to maintain, it's going to stay energized even when I release this button. Okay? And it will stay energized until a limit switch is activated. Okay? So I know I got a coil that's coming over here, so let's put this ruler back and line this up. I'm going to draw this line across. Oops, I did the eraser. My bad. Let me put this back. There we go. Okay, so I got that. I'm going to continue. I'm going to leave a little space for the limit switch though. But I do know that I'm going to have a coil of some type. Relay, a contactor. Again, it depends on the rating. Let's leave a little space and I'll just finish off this rung. All right. Okay, so I know I'm going to have a coil. That's what's going to be turning my light on and off. That's really bad. I was going to say, don't worry about the freehand, but that was hideous. Okay, even that's hideous. I always draw my connection points. Right, it tells me it's connected. Right. So if let's just say this, if I did not have this gap here and I push the button, you understand that because I'm trying to get to this lower potential across the DC comm, I would have current flow through here and it would energize this coil. Right? That's my load. But there's a limit switch that will not let that happen. Well, let me back up a bit. This needs to stay on somehow. Let me just put this in here. I'm just going to put this jumper in here. Right? So we know that when I push this button, this energizes. But it needs to stay on. Okay, so I'm going to go down a rung. And before I do that, I told you this was a relay or some kind of, yeah, a relay itself. We should always tag or name our devices. I'm going to call this CR1 for control relay 1. Okay? And the terminals, all right, are typically for a relay A1, A2. They could be numbered as well. You have to look at the spec sheet. And for a normally open push button, terminals would be 3 and 4. I'll show you that. Where am I getting these numbers from? Well, let me show you. Whoops, back that up. All right. Well, for the push button, here's a graphic. So there's 3 and 4, normally open. That's what the NO means. NC means normally closed, and they use terminals 1 and 2. Again, depends on the manufacturer and depends how many you stack up and stuff. But typically they're pretty standard. Notice the color too of the button. So this is the back side of the push button. It's green. Green is a standard color in controls for normally open. Red is their standard color for normally closed. So even if this was worn off, this NC and NO, and I've seen these colors in here, well, one, I'd know right away, okay, well, green normally open, red normally closed. And another way, of course, is you can use your meter and ring it out. Just do a continuity check, push the button, open the contacts, or close it and see what happens, right? You're either going to have continuity or you're not. Right, so there's where I was getting my numbers for the push button. And then for the relay, I like Finder. They're a great product for relays. I might start doing videos too on, you know, product reviews. But I typically use Finder for all my controls design and panel builds I do. Anyways, we'll just look at this 5513. There's the numbering. So I wrote A1, A2. Again, you can also use 13 and 14. These are standard numbers, right? So most manufacturers will follow this scenario. So I could have put 13 and 14. I chose to use A1, A2. A2 is always your DC comm or your neutral side, right? This one is a 3-pole double throw arrangement, right? We got 3 sets of contacts. Each set has a normally closed and a normally open, right? I like to use the numbers 11, 21, 31, 12, 14, 22, 24, 32, 34. It's easy for me because the first number tells me, okay, 1, this is my first set of contacts. 21, okay, the 2, that's my second set. 31, this is my third set, right? Because we got multiple sets on here. And if you're doing a diagram that you're using all 3 sets, okay, well, what set am I attaching my wires to, right? So I like to use these ones, but is there anything wrong with going, saying 7, 8, 9? No, right? It's the same thing. But we can see here that 11, between 11 and 12 is a normally closed set of contacts. Meaning when this coil is not energized, I got current flow through here. As soon as I energize the coil, this blade shifts over. Now 11 and 12 become open, and 11 and 14 close. 11 and 14 in its resting state or normal state is then normally open. All right? And it's the same idea for the other 2 sets. All right? So that's where I get my numbering from. So for mine, I know I'm going to want 11 and 14, and you'll see what I mean when I do my diagram. Okay, so I'm going to go back to here. I am going to draw. I'm going to use a set of contacts off CR1. Okay, so I'm just going to come out here, my next rung. I'll just leave a little space, come across, and then I'm going to go up and terminate this. And don't worry about the freehand this way. Terminate that. Draw my schematic symbol for a normally open contact, and I said I'm going to use 11 and 14. This is very important, everyone, to label, especially for troubleshooting. Imagine a guy coming in 5 years later and he's trying to troubleshoot, you know, your control diagrams. And of course, this is very basic what we're doing, but times this by 50 pages, right? Detail, you got to detail everything. Okay, so I chose to use 1114 because on this relay, those are normally open contacts. What else you should do is, what contacts is this associated to? Well, this is coming from my CR1 relay. So you should label that too, because you could have multiple relays in this circuit, right? Okay, so what contacts do these tie to? In my case, 11 and 14 on CR1. All right, so everyone can see what's going to happen here. If I push this button, this will energize, meaning these contacts will close. Therefore, I also have a parallel path of current flow through here, right? When I let go of the push button, well, this maintains current flow So this is never going to open or turn off. That's where limit switch 1 comes into play. Okay? So we need to put in a way to open the circuit, more or less. So if I erase this, and why am my clear canvas not coming on here? There we go. I'm going to throw in my limit switch here. Okay? And it's going to be normally closed because I want it to maintain. I want this to maintain until it's been activated, until whatever, maybe it's something on the machine that hits it, right? And then when it makes contact, we unlatch the circuit. So if we look at this now, the way the current flow is, and let me just change it up here. When I push the button down, current will go through here. It will continue through my normally closed limit switch, and I forgot to name this. And you would have to look at the spec sheet, but typically on a push button, it's 1 and 2. I'm not sure what it is for a limit switch, but again, you want to label your terminals. But regardless, I'm going to go through the normally closed limit switch. This coil becomes energized and continues back to the power source. Because this coil is now energized, the contacts associated with it change state, and in this case on 11 and 14 are now going to be closed. Now current also goes through this way. Right? As soon as I let go of the push button, the coil stays energized because current is still maintained through here, through this second branch, until I open this limit switch. Once I break this, I open the circuit, and that de-energizes, that will de-energize the coil. Therefore, the contacts open back up. I'll just redraw that. The contacts open back up, and now we have no current flow in the circuit. So it's a latching circuit, or you can call it low voltage protection, but latching circuit. Okay, so if we go back to the text, and I hope this is making sense for everyone. That's it, as basic as you can get. Okay, and I should also label push button. So I'm just going to call this push button 1. Okay, it says the light. Whoopsie, hang on. The light will remain on until roller limit switch 1 is activated. Okay, cool. So I'm going to go to another line here. And yes, I know some people are going to comment, well, you can just come off of here. I can extend off of this branch. Yes, I can. I like to break things apart when people are learning. So I'm going to create a separate branch. And I'm going to use another set of contacts off CR1. CR1. And I'm going to use the second set. So I'll say 21 and 24. And I'm getting a little ahead of myself. I want my ruler so to make it somewhat straight. Okay. Come across. And I will draw my NEMA symbol for a light as best as I can for a circle. Right? And I don't know, it'll be green. Light. Back to DC COM. A1, A2. Okay? So, let's go back to how this works. Push the button down. This closes. I have current flow through here. My limit switch is normally closed, so it continues on. CR1 energizes, which means this closes, this closes. My light now turns on. Right? I released the push button, but that's okay because when CR1 energized, I created a secondary path of current flow. Right? So now my push button is not being pushed, and that's fine. Why does this never come on for me? There we go. Right? I no longer have current flow through here, but I have it through here. Until this guy opens up. When the limit switch opens up, I de-energize the coil. I no longer have current flow through this branch. And because I've de-energized the coil, all the contacts return to their normal position. And again, 11 and 14 and 21, 24 in its normal state are normally open. Okay? So really, that's how you would do this one, right? It's not difficult. You just gotta kind of speak it out as you do it, right? But that's how you would interpret that and represent that in a wiring diagram. Okay, cool. Let's do two more. And actually, we'll probably do one more because I don't want to make these videos too long, right? So let's see here. Let me pick one. So stay on, both are released, remind to stay on push button are pushed and either one is released. Okay, let's just do the second one. Actually, we'll do the third one. Right. Okay, same idea. We need a power rail. Whoops, get this 90 degrees. Okay, zoom in. And you know what? Well, I'll just do this as 120 volt. So I'm going to make this red. It'll be red. Hopefully we can see it. So let's do 120 volt controls. And I want that a lot thicker than that so you can see it. Okay. So we got line 1. And over here we're going to have our neutral. Okay. And then I'll just label it. So this is neutral. And sometimes you'll see neutral represented as the number 2. This would be number 1 over here. But I'm just going to write in 120. Again, it's just the concepts. Okay. 120 volt. This one would be. It says a light will illuminate and stay on if PB1 or LS1 is pushed. Right? So that tells me that normally the light's not on until you push something. So normally open. So if I take, whoopsie, take this, it's an OR condition, right? PB1 or LS1 is pushed, not and. So I will start with my 120 volts over here. Draw my little circle, say it's connected. Actually, I'll do that after. So I got a push button that will go in here, and it's going to remain on. So I know I have a coil, and there's a push button 2 that will happen to deactivate it. So it's very similar to the first one. So I know I got something to unlatch my circuit. Okay, and then this will be on the other side. Okay, and I like to show my termination points. It's a good thing to do to show that it is connected. And then the other side, connected. Okay, I'll just do my devices in a different color. How's that? Let's see here. I'll just make them orange. Okay, so it doesn't look much different than red unless I zoom in. There we go. Okay, terminals. It's a normally open push button. Okay, I'll freehand this. Again, let me back this up. This, if I were to do this, this is not a normally open push button. Even though there's space in here, even though it's an open circuit, this is not a normally open. This would be considered a normally closed held open. Okay, so make sure when you're doing a normally open push button, you're actually showing it as you should. So the push buttons, the blade goes on top of the terminals. Okay, and normally open, so that is going to be 3 and 4. And this will be PB1. Okay. I know I have a normally closed button that is going to unlatch my circuit. Again, don't draw your normally closed like this, because that's really technically a normally open held down or held closed. Right? Normally closed, the blade is on the bottom side of the terminals for push buttons. Limit switches, it's reversed. This will be PB2. Okay? And then I have, because it's a latching circuit, I know I'm going to be using a relay, so I'll put a light in here. I don't know what color we'll make it. Let's see here. Whatever shows up nice. Let's do this color. There's my nasty relay. We'll call it CR1. That could be CR whatever. A lot of times when you get AutoCAD drawings, the relay will actually be, it will represent the line number that it's on. So if I was on page 1, line 1, I'd probably call it CR101. But for simplicity, this is just CR1. A1, A2 is what I like to use. You could use, what was it, 13, 14. There's nothing wrong with doing that. All right, if we go back to the schematic, I could have used 13, 14. All right, notice that this here too, they show this in IEC, not NEMA. And I'm doing my diagrams in NEMA. No big deal. It's the same logic. Normally open, normally closed in a coil. Okay, so latching circuit. But there's two items that will cause us to energize. Okay, there's also the limit switch. Okay, so get my ruler back out, go down another rung, and I'll use my red. So I'm going to draw a limit switch because that's another condition that will cause this to close. Okay, and I'll come up here. This push button would be 1 and 2. Okay, so terminals for my limit switch is normally open. So I'm coming down here. We'll call this LS1, right? Now, the way this is, will this latch when I push the push button or close the limit switch? The coil will energize, but will it stay energized once these are released? No. We need to latch this in. Because right now, you're only going to have current flow when you close these two buttons, and they're momentary. The push button is momentary, the limit switch, it could close and stay closed maybe for like 5 seconds, but whatever is activating it might come off of it and it will open up. And maybe you don't want this relay to de-energize when that happens, right? So we need to latch it in. We'll use the contacts off that relay to latch it in. Right? So again, just come off. Come here. Bring this down. I know it's not perfect. Oops, I can go there. There we go. And I'm going to use a set of contacts for my CR1, and I'll use 11 and 20, or sorry, 11 and 12. Okay. And then we're still doing a light, right? So I'm going to draw this one differently, right? Yes, like in the first one, I could draw a different rung, but for those that, you know, want to see it this way, I can come off of here. That's no big deal. And draw my light. We'll make this one red. This one was green. A1, A2. Okay. No big deal. Whoops. This is the same thing as doing this. I'll do it in a different color, but this is no different than if I created a second rung and just came off of 21, 22 to the light. No different. Right? When you follow the current. A2. No difference. Because when you examine the current flow, right? Let me just use a slightly different color here. I use green. When this button closes, right? I would have current flow through here. This is normally closed. This turns on my CR1, which means this closes and current is coming down here. Now I have a path through here that would turn on the light. No different than if I just showed it like this. This would close because it's CR1. I'd have a path through here and it'd still turn on the light. Okay. Same thing for, whoops, too far, or I just came off. No different than, let me label this, for this one here. So if I closed LS1, well, it's going to come through here now instead. Okay, instead of through the push button. Still going to come through here, latch it in. Oh, shoot. Still going to latch it in It doesn't matter which way I do it, same idea. Current's going to go this way, going to go this way. Even when I close or open limit switch back up. I open up the limit switch, right? Current's no longer going through here. But because this was energized and this closed, that means now our current path just maintains through here, or here if you drew it this way. No difference, right? It's the same. It's just, if you can understand how current flows, this will become second nature. Like this may be daunting at first, but if you can just understand basic theory on current flow and understand that you're just trying to get from two different potentials and you just got a little bit of work to do in between that, right? Because if you don't, then you just got a short circuit. Then, you know, it just comes down to how efficient you draw, whether it's an AutoCAD or just a hand sketch, and how easy it is to read it, right? Because you want the guy to be able to interpret it and read it fairly simply, right? So that's how you do that one. You know what? I will do the second one just really quick. Just why not? I'll just do it all freehand, really quick. All right, so this one I will do in 24 volt DC, so I'm going to use those colors. I wish this blue would show up nicer because you will get into, when you're doing DC controls, blue is 24, and then you'll get into white with blue stripe or blue with white stripe for the COM. But that's another story. I'll just do it all in blue. So right off the bat, you need some power rails. 24 volt DC for mine, 0 volt DC. This is saying a light will illuminate and stay on if PB1 and LS1 are pushed and either one is released. It will remain on until PB2 is activated. Again, it is a latching circuit. So I got PB1, draw my terminals, I push that one. Now this is an AND, so I also have to close a switch, a limit switch. So in PB1 and LS1 are closed, right? A light will activate and it will stay on until PB2 is activated. Let me back this up a little bit because I leave myself enough room. Okay, so it tells me there's something that will deactivate my circuit as well. So now I need a normally closed push button. Make sure it's actually closed. Well, it's getting sloppy. Trying to draw. Let me zoom in. That'll make it better. Now it looks more like a cartoon. PB2, which should be 1 and 2. Now I'll draw my coil. CR, I don't know. We'll call this CR5. Doesn't matter. Give it something, right? And again, normally these devices are addressed or labeled according to the page and line number that they are found on. That makes it easier for troubleshooting purposes, right? So you see a device that says CR125. Well, you know in the prints, just go to page 1, line 25, and you'll find it in the schematic. Okay. So this one again, it's a latching circuit. So I know I need to latch this puppy in after my initiating devices here. CR1. Oh, actually we call this one 5. And 1121, right? Again, I could put my light off of here, but whatever. I'll put it down here. I'll use another set of contacts off of CR5, right? Connection point, connection point. We'll make this one yellow. A1, A2, CR5. I think, hang on a second, 11 and 13, I did this one wrong. It's 11 and 14. This is 21, 24. So that's how you do that one. But again, if you understand current flow and you understand that you're just trying to get from two different potentials, you just have to go through a few obstacles, do some work, and then get back to the source. This is easy. If you understand current flow, these are not hard to create or troubleshoot. Okay, so I hope you like this first video of a control topic on my channel. Again, I want to do a lot more of this because I do a lot of controls, not just code book stuff. So let me know what you'd like to see. I do want to also add a section for product review, so that'd be cool to do as well. So we'll just see how this channel grows. All right. So I hope you enjoyed it. Let me know what you think of this. All right. I really appreciate the feedback. All right. Cheers.